in this exercise number 4 is asking you to calculate the ground level concentration and the distance at the maximum ground level concentration and the distance at which it occurs. Okay, for me, for example, if you ask me where is the maximum concentration at the ground level, you will suppose that Z is equal to 0, صح ولا لا? So in this equation, you will consider Z equal to 0. This is one thing. The second thing you will consider, if you are at the x-axis, y equal to 0. So this will simplify the equation. What remains in your equation is m point divided by 2 pi u sigma y sigma z. هنا 1 وهنا عندك 2 ضرب exponential minus h minus half h divided by sigma z squared. Isn't it? Yeah. So I'm inviting you to draw this curve. I would like to draw the curve. And I will show you mathematically how to do this. Mathematically, you need to derivate. To find the next term, you need to derivate. But to simplify the process of the derivative, you can pass to the log, one of the techniques. You pass to the log, so you simplify a lot of things. Because the derivative of log is a sum. The product. If you pass to the log, you have a sum. So it's easier to calculate. Okay? The maximum of this equation is the maximum of the log of x, because the log is a monotone equation. So this is one way. You can derivate this directly. There is no problem. To derivate this, where is x? X is hidden in sigma y and sigma z. When I'm gonna make the derivative, dc على dx, I'm gonna say that this is c of when I do the derivation, I'm gonna do dc على d sigma على d dx. I can do this because it's like g rho composite with f. So the derivative is f dash g dash of f. I can do it like this, but it's easier to pass to the log. Okay, so I'm proposing, before, since we are programming a little bit, I'm proposing to show you the curve of the concentration at x equal at z equal 0 at the center, at x-axis, at the ground. So what I did in reality is the following. So what I did is the following. So this is my equation. Okay, this is my. Should I enlarge this a little bit? So this is my equation. See, even the time we are averaging in reality, the time is an average time. Maybe I should remove the time. Okay, because in reality we are averaging every 10 minutes. We are making this. There's a standard that you can find this in the literature. So, because I don't need this. Okay. So C x y equals 0, z equals 0 is equal to m points divided by pi u sigma y sigma z exponential minus h2 divided by 2 sigma z2. So what I did is the following. I would like to just tell you that in reality, sigma y, if you take an atmospheric class T, sigma y is equal to a constant. The coefficient A and B are constant, and A is equal to 68, will be equal to 0.894. But if you look at sigma z, it depends on x. Okay, so you should when you program this, you should consider, you should do an if. So what I did is the following. I imported pi and exponential, but even exponential I don't need it because I used NP exponential because I used NumPy library. So I imported NumPy because I will work with vectors. So for that, a sigma y vector, I will draw through x. A sigma y is a function of x, or sigma z is a function of x. الاثنين function of x. I'm gonna plot this to show you the result. بالنسبة لل A 68 ال B 0894 صح ولا لا؟ جميل. الإيميشن ريت هو 110 جرام per second. So that's why I'm multiplying later on by 10 exponent 6 to have a result in microgram. السيجما واي يقول لك الاكس should be in kilometer. This is mentioned in the exercise. Huh? Where's so x in kilometer and the result sigma y and sigma z are in meters. Okay. So otherwise you will have a wrong result. So that's why I'm dividing هنا في sigma y. I divided first of all x as a vector starting from 10 meters from the chimney. You can start from 1 meter. It's not a big issue. I can start from 1 meter. يعني I'm avoiding having a division by 0 in my equation. That's so in sigma y because you have ax exponent b. So I'm just avoiding this. I'm starting from 1 meter, okay, to 20 kilometers, just to see the distribution along the x-axis, and the time, the x step every 10 meters, okay. So this is my vector x. A sigma y هي ax exponent b, but x should be in kilometers. So that's why I'm dividing by 1000. بعدين هنا قلت this is one way. It's not maybe it's not the best way, but it's one way. It works for me. I solved my problem, but it's up to you. You can do better than this. بالنسبة للسيجما Z, it depends on the distance. For x less than 1 kilometer, you have coefficients C, D, and F. For x bigger than 1 kilometer, you have another value for C, D, and F. So that's why I didn't use the same logic here. And another point, I should define sigma Z, otherwise maybe I have a problem. أنا عرفتها كأصفار في البداية. So sigma Z is equal to NP dot zeros of length of x. يعني a vector بطول x لكن أصفار. تمام؟ To define it, it should be defined. بعدين هعبيه, I will fill it with the corresponding values in this loop. So in this loop, what I'm doing what? I'm saying that for I going from 0 to tall vector x, if x of I is less than 1000, is less than 1 kilometer, I should take C equal to 33.2 because in my table here, if x is less than 1 kilometer in the atmospheric class D, C is equal to 33.2, D is equal to 0.725, والF is equal to minus 1.7. بالنسبة للX bigger than 1 kilometer, you should take this C, this D, and this F. So for that, I created a loop. So I'm starting from 1 meter, X, I calculate sigma Z. The first, طبعا هنا I'm dividing by 1000 because it should be in kilometers. So else, if x is bigger than 1 kilometer, you should take these values. Yes. Let's continue. A and B here. The A and B are used for sigma y. خلاص بالنسبة للسيجما y I finished the job. For sigma z, I define my vector sigma z. I initialize the vector sigma z to 0. So it's a vector full of zeros. Okay. So now if maybe I'm gonna just resize it a little bit. So if xi less than 1 kilometer, this is C, D, and F. I calculate sigma Z of E for the corresponding X, okay, for Xi, for the value Xi. It's a vector. Exponent D plus F. Else, C is equal to 44.5, D is equal to 516, and F equal, and I calculate my sigma Z, okay? So after doing this, after doing this, I'm just I don't know, maybe it's not mandatory to do this. Maybe this is maybe this line is not mandatory. ممكن أشيلها يعني. I can comment it, I think. Since I'm defining sigma Z as an NP vector, I don't need it to mention this again. Okay? يعني point divided by pi. Pi, you have two ways to define pi. The first way is np.pi, because you are calling already the NumPy, or since we are calling it from math here, same thing, exponential, you can use NumPy, or you can use the exponential from math. But why I don't use the exponential from the math library? Because I'm manipulating an NP array. I'm multiplying vectors. If you don't use the NP library, the NumPy library, you will have an error. Automatically you will have an error, and we can try it. So if you keep it, because here you are dividing a real value by sigma Z, okay? If you use exponential like this, you will have an error in your calculation, okay? You will have an error. Why? Simply because exponential, you are calculating the exponential of a vector, okay, and multiplying this by another vector. So to be understood by Python, you should use it as an NP array. If you are using an NP array, you are on the safe side. If you run the exponential, sorry, we need to try to run it again. Okay, so if you do the calculation, so I calculated sigma y, sigma z. I calculated the exponential. So I've already called the library here, the library matplotlib.pyplot as PLT, just to draw my results. So I define my figure as figure 1. This is not mandatory to do this. This is not mandatory. But why I use this? Because in the practice, if you have a lot of figures and you can call them a lot of times, it's better to give them tickets, names. Okay, I can call it instead of 1, I can call it another 1 as a string, plt.figure, another 1, and it works. In MATLAB, it doesn't work. You should give numbers. Okay, and you can do a lot even for your figures. So for the plot, I'm plotting x, c. صح ولا لا? In dashed black, I prefer this. For the label, x is in meter, and for the concentration, I'm using char 956 just to make the mu appear. But I think since and between dollar هنا, just to make the cubic meter as exponent, I'm using latex هنا. حتى هذه ترى ممكن اغيرها انا، ممكن I use slash mu and it works. So like this, when you run it, your results will be like this microgram per cubic meter. It's more يعني in terms of aesthetics is better يعني. So that's why. وhere x. So if you look at your figure, the maximum is somewhere here. Okay, somewhere between 2,000 and 5,000 meters, and I kept x in meter. And I just divided by 1,000 in the calculation to keep x in meters. So as you see, you have this maximum here. Okay, so the maximum is c dot max if you want the values exactly, and the x max is x of c dot arg max. يعني c dot arg max هذه بيدي لك وعندنا سي 0 سي 1 سي 2 سي 3 حتى سي اخر واحده، هو يدي لك الاي هذاك العداد متى تصير ماكس. فاذا تبحث عن الاكس تبعها خلاص تحط الاكس تبع السي اوف ارج. فانا بحط اكس اوف سي ارج ماكس. متى صارت السي ماكسيموم؟ بحط الاندكس تبعها. فبتدي لك ايش؟ بتدي لك when you run it. Oh, sorry. When you run this, you obtain x equal to 2,891 meters, and the concentration there, not in ppm. I'm doing a mistake in microgram. So I can use directly this. Okay. Okay. خلاص. Microgram per. Certainly, if you want to find exactly this the value, I just want to run this again. Sorry. Okay. So just to find this maximum, one of the ways, I don't know, maybe you can define, for example, n0 equal to 100, n1 equal to 1,000, 5,000, and here you plot your x in a range. Okay, so you can yeah, put here n0 to n1, and I'm gonna copy paste this here. So like this, instead of drawing my curve along 20,000 meters, I can, oops, maybe I need to run this again, all this. Okay, this is good. You need to update. So you see, this is your maximum. You can also add here, for example, one of the non-fungible grid. Okay, so you create a grid. So if you run this, okay, so if you run this, you see that your maximum is somewhere here. It's a graphical method. Okay, it's not very accurate, but you can tune the values. You can put, for example, here, for example, between 2,000 and 4,000, and try to you know, I'm gonna run on the cells. This is my maximum. So it's somewhere between 2,750 and 3,000. You can go further, and you can take here, for example, something like this. This you put 3,000. I'm gonna run all the cells in order to. So this is my maximum. It's somewhere near to 2,900 meters. So x max. This is the graphical method. Okay. So x max. Okay. So it's about. It's between. Yeah, it's somewhere between 2,850 and in meters. So this is your x max. Your c max also you can tune here. If you go further, if you put even this value, you can put like this, 700 to 900, for example. Okay, something like this, and run all the cells. And, you will find that the maximum maybe here 3,000. If I put 3,000, okay, and run it to run all the cells. Okay, so I have a value about 1. So my Cmax is equal to, okay, 183.6 microgram per cubic meter. So this is the concentration if you want to calculate it using a graphical method. It is better certainly to do like this, to calculate Cmax from the city, okay, because if you calculate Cmax, you will find directly the value of, if you find the maximum concentration, and here from the C arg max, okay, you will calculate this is the index, you will find the X max. And I think this is the best way to do it. If you have a series of data, it's better than doing it graphically. So this is the first way. This is the second way is using the formula we have in the slides in the book. Okay, so as we said, we have this formula, okay, giving you a correlation linking CU divided by Qmax, and this one is given also by this nomograph. We will see now how to use this graphic giving you X max and Cu divided by Q max and this correlation. Good. So let's go back to this. So this is my relations exponential. So I'm defining it as alpha beta. So alpha, this is taken from the book. We can open the book. Oh, this is, sorry, we go to the assignments. So this is the book. So we have a formula for this. Yeah, this is the table, and you have also the values corresponding to this. Okay, corresponding to A, B, C according to the atmospheric class. Okay, this is the values of A, B, C, D. Okay, but in our slides we define this as alpha, beta, gamma, and delta instead of A, B, C, D, because sometimes there's a certain confusion between these values and the values of the AB of the atmospheric class. Okay, so that's why in our slides we define them like this. So we will use these values here. Okay, so this is for a atmospheric class D. Okay, I'm gonna remember this. So atmospheric stability class D, you have these values of alpha, beta, gamma, and delta, and you can calculate A, which is equal to this thing, okay? You can define it as a function or numerically. So I calculated this. After this, I'm multiplying by m point divided by U, cross 1e6 to get a result in microgram per cubic meter. And I can copy this again. I like it here, just to get a result in with the correct unit. Okay, so if you run this, okay, so this is the value. Okay, and certainly, so you have, this is your concentration, the maximum concentration at the ground. I'm gonna run all the cells. Okay, now if you want to calculate the value graphically of Cmax, you have to open this file. I sent you this, I think. So I sent you this Cmax. So, and you specify, I'm gonna delete this and just without deleting this, I'm gonna talk about it. So this is my graphic. Maybe I'm gonna redraw this graphic again using a log scale in Python. But in our case, we have an atmospheric class D. We have an effective stack height of 10 meters. So when you project this here and here, you have about 2 kilometers. Okay. So this is the value almost of 3 kilometers. So you have almost x equal to 3,000 meters. Okay. So this is for the, so as you see, it's not really precise when you do it graphically, but you have almost an error about maybe half or maybe less a little bit of a kilometer, maybe 250 meters. Okay. And if you project here, so here 10 exponent minus 6, here you have 10 exponent minus 5, 9, 10 exponent minus 6, 8, 10 exponent minus 6. So you have a Cu divided by m point max equal to 8, 10 exponent minus 6. So if you come back to your thing. So that's why I brought this. So this is obtained. This was obtained from the graphic. Okay. So now, if you take this value and you multiply this by n point 10 exponent 6 to get the result in microgram per cubic meter, and you divide by u, this is the speed, the wind velocity or the wind speed at the stack height. So it's given in the exercise. So it gives you a result of this 176 microgram per not. There's an error here, per cubic meter. Okay, so, yeah, there's a little difference, and certainly the result we obtained here, okay, 183 is more accurate. So this is concerning the two methods. So now, if you're gonna work in an exam or something like this, and you work on paper without computer, you will have the you have the possibility mainly because this will take a lot of time to draw the curve, and I will not use the graphic method. I will prefer this method or this formula or this graphic. So what is good in this graphic is that it gives you directly the value of x max and cu divided by q max. Okay. What else? Also, I'm gonna close this. Okay. So I'm gonna continue. I'm gonna show you another thing. So this is concerning the graphical approach. So the last way is I would like to show you a method. So look, in general, in our case here, I'm gonna take this. This is the last method. So here I'm gonna go and put n0 to 0 and to length of x. Okay, just to come back to our original graphic. Okay, can I? I'm gonna copy this image. Okay, and take it to Paint. I just want to explain something. Sorry, this is Paint. This is Paint. Okay, so in this case. I would like to use a library called the SciPy. In this library, you have the possibility to find the minimum of a function. In general, in engineering, even if you want to find the maximum, in reality, we transform the problem to find the minimum. And this minimum, we would like to find the maximum of this mathematical function. Okay, I'm gonna remove this, but instead of calculating C, I'm gonna move the endpoint here, the U, so CU divided by Q max, I'm gonna call it the function calculation or C modified, which is equal to 1 divided by pi sigma y sigma z exponential minus h2 divided by 2 sigma z squared. And I'm gonna calculate mathematically the maximum, this maximum. So since this function is positive, and in general we try to minimize, to find the minimum of function. Instead of calculating this, I will calculate it minus this function. Okay, the minimum. For that, I'm gonna do the following. So I'm gonna come back. So this is the I defined the function called calculate C. So here, in reality, we calculate for the atmospheric class, for the value of U, etc. Sigma Y, sigma Z, we have a hatch, an H value. And here, as you see, I'm calculating, I'm returning from the function, from this function, okay? So it have as input X, and in the output, you have 1 divided by pi, sigma Y, sigma Z, exponential minus half, H divided by sigma Z squared. And I will not use this function. I will use minus this function because I'm gonna minimize this function. I'm gonna find where's the minimum. So so what I did. So this is the graphical function. I don't need it. Okay. So you can use just you can call the function. How to say this? You can define an x0. Okay. I don't need to. I'm gonna remove all this. So from SciPy, I don't need to plot anything. From SciPy dot optimize, I'm gonna import the function minimize. I'm gonna put an initial guess equal to x0 and try to minimize the function calculate C2, which is minus calculate x, which is minus this value. Okay, so this it will be the inverse of this. Okay, so it will be something like this and goes negative and come back to increase. So I'm gonna write it like this and use a method called Nelder mean just to optimize this. So this function will try to guess, change the value starting from x0 until it reaches the output, the minimum. Okay, this minimum, the minimum of minus calculate c, will be the maximum of this function, which will be x max, our x max. So we will be able also to calculate c max. So I'm gonna run this. So when you run it, you obtain minus 834. So in reality, we don't obtain something like this, but I'm gonna show you what we obtain. In reality, we obtain something like called an output. I'm gonna print output just to make you understand what happens. So print output just to see the shape. So in reality, all this is the output, okay, of my optimization. It's a dictionary. So you have a message, optimization terminated. The success is true. The state is 0. The minimum of this function is minus 834 10 exponent minus 6. So if you multiply by 10 exponent, you will find something in microgram later on. The value of extrema, minimum or maximum, is 2,895, and the number of iteration to converge is equal to 33, and I don't know, and then this is the final simplex of your calculations. So this means that if I would like to calculate to grab x from this output, I have to write for the output of the function, you will have this value, and to get x, you should write like this. And the output of x in reality will be a list. So you should put list of 0 because this function can be used for multi-variable functions. Okay, yeah, you can optimize f of x and y or f of x and y and z. So that's why I calculated x max, and this x max, I take the value 0 to grab the value. And this permits me to calculate the concentration in microgram, and I present my results. So I'm gonna just hide this and run again. So these are my results. The value of x max, and this is the most accurate result: 183.6 microgram per cubic meter. Now this result, if we look back, we have here, for example, for the graphic 176, 182.5 for this method. Here, for example, 183.6, 183.6, 183.6. Here we calculated the maximum without optimizing. We draw the curve, and in your city we found the maximum. This is in the graphical method, the result 183.6. We try to find it like this. So this is what I would like to say for this exercise. I hope you enjoyed. So I used the function minimize. Okay. In the next exercises, I will try to use this same library, but I'm gonna use another function. Okay, called fsolve. But fsolve the function f solve. Okay, f solve in reality solve the problem f of x equals 0. Okay, in this case it's another problem. You are trying to find the minimum, which is completely different. Okay, thank you, bye bye.